Astronomers in Durham have made the biggest ever computer model of the evolution of the universe from the Big Bang to the present day.
Deep within NASA's cutting-edge research center, a machine that challenges the boundaries of conventional computing recently experienced something so astonishing, so unprecedented, that NASA had no choice but to shut it down. Envision a world on the edge of reality, where the advanced technology we rely on opens a doorway to the unthinkable. What occurred behind those locked doors? What did NASA's quantum computer uncover that led them to pull the plug? Join us as we explore the enigma of NASA's quantum shutdown, venturing into the farthest reaches of human knowledge and stepping into realms where science fiction converges with reality. Quantum computers are like the rock stars of the tech universe, jamming to the rhythm of quantum mechanics rather than the conventional computing beat. Unlike traditional computers that deal with binary bits, zeros and ones, quantum computers use qubits. These qubits throw an epic party, holding both 0 and 1 at the same time, thanks to the phenomenon known as superposition. They're the VIPs in the quantum computing scene, pulling off a trick where they exist in multiple states at once, making it possible to perform many complex computations simultaneously. Quantum computers are the rebels of the tech world, using qubits' mind-boggling properties to process information in ways that seem otherworldly. It's like they're leading a technological revolution, and everyone is invited to the quantum bash. Traditional computers stick to a strict binary code, processing either 0 or 1 at a time. But quantum computers defy this logic by exploiting superposition and entanglement, allowing them to juggle multiple tasks simultaneously. If you're wondering how this quantum revolution began, let's rewind to the early 90s. It was then that quantum theory made its entrance, shaking up the scientific community and igniting a new wave of discovery. Scientists embarked on a thrilling quest to tap into the full potential of quantum computing, delving deep into the building blocks of our universe, atoms and subatomic particles. Back in the 1920s, Max Planck introduced a groundbreaking idea, revealing that energy doesn't flow continuously, but rather comes in small packets. This insight became a key part of quantum computing's rise. In 1925, Werner Heisenberg added another twist to the quantum puzzle, presenting the uncertainty principle, which states that it's impossible to simultaneously know a particle's precise location and momentum. The quantum world, as we now know, is full of paradoxes, keeping scientists on their toes with its unpredictability and probabilities. Fast forward to 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen revealed the EPR paradox, which introduced the bizarre concept of quantum entanglement, challenging classical physics. The quantum realm, it turns out, is not just odd, it's revolutionary. In the 1980s, quantum computing began to move from theory to reality. These machines, powered by quantum mechanics, promised to tackle calculations far beyond the reach of regular computers, leaving conventional devices behind. Quantum computers seemed almost magical, able to perform tasks that regular machines could never dream of. In 1982, physicist Paul Benioff had a eureka moment, envisioning a machine that used quantum mechanics to perform computations. This sparked an idea that quantum computers could far surpass traditional computers, setting the stage for a technological gold rush. The excitement didn't stop there. In the same year, physicist Richard Feynman caught the quantum fever and expanded on Benioff's idea. Feynman imagined these quantum computers as the ultimate problem solvers, tackling challenges too complex for classical machines. His enthusiasm ignited a fire in the scientific community, propelling quantum computing into the mainstream. By 1994, mathematician Peter Shor dropped a bombshell with his algorithm, capable of factoring large numbers much faster than traditional computers. This revelation unlocked quantum computing's true potential, setting the stage for its widespread application. In 1998, a team at Los Alamos National Laboratory achieved a breakthrough, creating a quantum computer with 2 qubits using nuclear magnetic resonance techniques. While this system had its quirks, it marked a significant milestone in the development of quantum technology. As the years passed, excitement surrounding quantum computing grew. In the early 2000s, teams from various labs and companies around the world started pushing the envelope, striving to create more powerful quantum systems. In 2021, IBM's release of their 7-qubit quantum computer, the IBM Q, sent waves of excitement through the tech world. Researchers weren't just working on new devices, they were also focusing on quantum error correction, which is essentially like creating a protective shield for quantum information against environmental interference. With techniques like the surface code, scientists began enhancing the reliability of quantum computers. In 2005, a group of brilliant minds at the University of Innsbruck and the National Institute of Standards and Technology built a real quantum computer, albeit a small one with just 5 qubits. This marked a turning point, showing that practical quantum computers were no longer a distant dream. By 2007, researchers at Yale University had improved stability and manageability by creating more reliable qubits using solid-state systems, making quantum computers feel more like the cool new kids on the block. Fast forward to 2010, and researchers at the University of Science and Technology of China achieved something straight out of science fiction: quantum teleportation. No, they didn't teleport humans, but they did manage to transfer quantum information between 2 particles located 10 miles apart. This discovery opened the door to building quantum networks, where quantum information could travel vast distances. In 2013, Google and NASA teamed up to develop the D-Wave 2, a cutting-edge quantum computer. Unfortunately, an unexpected government shutdown disrupted the project, putting the quantum leap on hold. When the government resumed operations, the D-Wave 2 was back on track, rekindling hopes for exploring the quantum frontier. In 2019, Google made waves by demonstrating quantum supremacy, the ability of their quantum computer to solve a problem that would be impossible for any classical computer. This fueled fierce competition, with tech giants like IBM and Microsoft eager to showcase their own breakthroughs in quantum technology. By 2020, IBM unveiled the IBM Quantum System 1, the first quantum system designed for commercial use. This marked a major turning point, bringing quantum computing closer to everyday applications and turning what was once a science fiction fantasy into a tangible tool. Governments around the world took notice, pouring funds into quantum research and development. Researchers, academia, and industry experts joined forces to advance the field, with new centers, labs, and initiatives springing up to harness quantum technology. Amid this global push, a fascinating theory has emerged in scientific circles. What if intelligent life exists on other planets, and these alien civilizations are using black holes as ultra-powerful supercomputers? These cosmic powerhouses could be used to process information at unimaginable speeds. Since the 1960s, scientists have been listening for signals from extraterrestrial civilizations. However, researchers from Germany and Georgia propose that we should expand our search beyond traditional radio signals, looking for evidence of directed energy, neutrinos, quantum communications, and even gravitational waves. According to physicists Jad Valley and Zaza Osmanov, extraterrestrial civilizations might be using large-scale quantum computers, and we could detect these alien technologies by observing black holes. These black holes, possibly engineered by superintelligent aliens, could be emitting radiation, including Hawking radiation, which is a form of energy predicted by physicist Stephen Hawking. The Ice Cube Observatory, nestled in the frozen depths of Antarctica, could be the key to cracking this cosmic mystery, acting as our Sherlock Holmes to uncover extraterrestrial activity. This theory offers a potential solution to the Fermi paradox, the cosmic conundrum of why we haven't yet detected signs of intelligent life despite the vast number of potentially habitable planets. If advanced alien civilizations are using black holes as quantum supercomputers, we might be missing their signals not because they're hiding, but because we're not searching in the right way. Instead of relying solely on traditional radio signals, scientists now suggest we should broaden our efforts to look for other signs of alien tech. As the quantum computing revolution progresses, it promises to open up new frontiers for humanity, from military advancements to safeguarding digital information. However, as quantum computers grow more powerful, they also pose significant risks. For example, quantum machines could threaten encryption algorithms, which are the backbone of cybersecurity. Classical computers rely on encryption to secure everything from banking transactions to government communications. But quantum computers could break these codes, putting sensitive information at risk, including the security of cryptocurrencies. To counter these threats, scientists are working on new forms of encryption, such as quantum cryptography, which relies on the principles of superposition and entanglement to protect information from unauthorized access. These new systems could form the backbone of a secure digital future, but they also present challenges. The world is on a race to build quantum-resistant encryption methods, ensuring that even as quantum computers become more powerful, our data remains safe. While quantum computing promises to revolutionize fields like space exploration, material science, and climate modeling, it also brings new complexities. Researchers are working to ensure that the powerful capabilities of quantum systems don't disrupt the integrity of scientific simulations or leak sensitive data. As quantum technology advances, experts are developing post-quantum cryptography to keep our digital infrastructure secure from the rising tide of quantum capabilities. This new form of encryption could become the ultimate safeguard, offering a shield against the vulnerabilities that come with quantum-powered breakthroughs. As we approach the era of quantum computing, a few fascinating questions arise. Will we see the day when quantum systems enable us to simulate complex molecules, unlocking new frontiers in drug discovery and material science? Or perhaps quantum computing will allow us to model the complexities of climate change with pinpoint accuracy, enabling us to develop solutions we couldn't have dreamed of with classical systems. The possibilities seem endless, and many in the scientific community are already imagining a future where quantum computers become integral parts of our daily lives, transforming industries and reshaping our understanding of the universe. Despite the promising potential, we still have a long way to go. Quantum computers are still in their infancy, with many challenges to overcome before they can live up to their hype. For one, the hardware is still unstable. Quantum states are delicate, and quantum computers must be kept at temperatures close to absolute zero to function. The qubits are also prone to interference, known as quantum decoherence, which can result in errors. These challenges must be overcome before we can reach the stage where quantum computers are reliable enough to perform large-scale computations in practical applications. To solve these problems, scientists are working on developing better error correction algorithms and stabilizing qubits. There's also the challenge of scaling up quantum systems, building computers with enough qubits to solve real-world problems. Quantum entanglement, a phenomenon where qubits become interconnected in such a way that the state of one qubit is immediately related to another, is one of the key areas of focus. It's this entanglement that enables quantum computers to perform many calculations at once, but harnessing it on a large scale remains one of the biggest hurdles in the field. Governments and private companies are pouring vast resources into quantum research, and some of the brightest minds are dedicated to this technological leap. It's likely that we'll see incremental improvements in the coming years, with more powerful and stable quantum computers becoming available. As this technology progresses, the potential for breakthroughs in fields like artificial intelligence, space exploration, and encryption will increase exponentially. However, the ethical implications of quantum technology cannot be ignored. As quantum computers become more powerful, so do the risks associated with their misuse, from breaches in digital security to the weaponization of quantum technologies. In the long run, quantum computing could very well lead to a dramatic shift in how we understand and interact with the world. By unlocking the potential of quantum mechanics, we may one day unlock the ability to simulate entire universes, or even harness the energy of black holes. What was once considered impossible could soon become routine. But as we unlock these unprecedented capabilities, we must tread carefully, ensuring that we remain mindful of the ethical, social, and political implications of these powerful tools.